We now move on to look at a different kind of pattern. Have a look at this pattern. 3, 6, 12, 24. What do you predict the next term will be? Hopefully you're noticing very easily that what we're doing each time is just doubling, multiplying by 2. So to get to the next term, we'll multiply by 2 and we'll get 48. And the next term after that, again, we'll just multiply by 2 and we will get 96. Now, we don't want to just carry on multiplying by 2 each time. We'd like to, for example, be able to easily answer what's term number 100 or what's term number 532. And to do that, we need to develop a formula for Tn. How are we going to do that? I'm going to use a table just to help me sort this all out. So I've written my pattern of, well, at least the first 4 terms of it into this table. And now I'm going to almost try and undo, I'm going to try and see what calculation did I do to get to the 6? What calculation did I do to get to the 12? So the 3 was just what we started with. What did I do to get to the 6? Well, I started with a 3 and multiplied by 2. So that's the calculation I did. What did I do to get to the 12? Well, I started with a 3, multiplied by 2, multiplied by 2. So I did 3, multiply by 2, multiply by 2. And what did I do to get to the 24? Started with a 3, multiply by 2, multiply by 2, multiply by 2. So 3, multiply by 2, multiply by 2, multiply by 2. Now what you're going to see is if I write this using exponential notation, I'll be able to spot the formula sitting there. This was just 3. This is just 3 times 2 to the power of 1. Here we've got 3 times 2 times 2. That's 2 to the power of 2. And here we've got 3 and then we've got 2 times 2 times 2. 3 2's multiplied together. So that's 2 to the 3. Now take a look here what we can see. For term number 2, we just have 1 2. For term number 3, we have 2 2's multiplied together. For term number 4, we have 3 2's multiplied together. So what do you predict we're going to have for term 10? Hopefully you said it's going to be 9 2's multiplied together. And if I asked you what would happen maybe for term number 205, hopefully you'd say, noticing the pattern, that it's going to be 2 to the power of 204. And that gives us the idea of what we're going to do for Tn. It's just going to be 3 multiplied by, not just n, it's going to be just the number that was 1 smaller than n. We're going to look at one more example of a pattern with a constant ratio. So if we have a look at this pattern here, 9, 3, 1, 1/3, 1/9, etc. One way to think about how we've gone from one term to the next is to think about it as we've divided by 3. So we could think each time we've gone, we've divided by 3. But another way of writing divide by 3 is to simply talk about it as multiplying by 1/3. And we're going to use this idea of multiplying by 1/3 because then we're basically going to be have the same story as we did the previous time. So let's see how it works out in a similar way. If we put it in a table, we can then see, like we did last time, that the first term is just 9. And the second term is that 9, but then multiplied by 1/3. And then the next term along is going to be that 9 multiplied by 1/3 and then multiplied by another 1/3. And then the next term, 9 multiplied by 1/3, multiplied by 1/3, multiplied by 1/3. And now if you write these as exponents, we are going to be able to see the pattern very nicely. This is 9 times 1/3 to the power of 1. This is 9 times 1/3 to the power of 2. And this is 9 times 1/3 to the power of 3. And funnily enough, this first one, just so we can also write it as with a power, is 1/3 to the power of 0 is just 1, right? So this is 9 times 1. So it's 9 times 1/3 to the power of 0. Now again, just as we did last time, we notice the pattern. When we've got term 1, we've got a power of 0. Term 2, we've got a power of 1. Term 3, we've got a power of 2. Term 4, we've got a power of 3. And so that helps us see quite easily that for term n, we're going to have 9 multiplied by 1/3 to the power of n minus 1. And let me write that nice and big there. It's Tn is going to be 9 multiplied by 1/3 to the power of n minus 1. So far we've looked at patterns where there's a constant difference. In other words, where you add or subtract the same thing to each term to get to the next term. And also we've looked at patterns where there's a common ratio. Those are where you multiply or divide each term by the same thing to get to the next term. We're now going to look at different patterns, and these are going to be patterns with squares and cubes. A reminder of what squares and cubes are. Squares are like 7 squared. 7 times 7 is 49. Cubes, 4 cubed, 4 times 4 times 4, which is 64. Really recommend that you know these squares and cubes that are in this table off by heart. It will help you both now and all the way through in your maths career. Let me show you why it's going to help you now. Imagine we have a pattern that looks like this. If you know your table well, you will look straight away at this pattern, recognize that what you're seeing there is squares, see that T1 is 1 squared, T2 is 2 squared, T3 is 3 squared, and so you will immediately be able to say that Tn is n squared. But let's have a look at some of the features of this pattern. Let me first have a look at the difference. In other words, what does it take to get from there to there, from there to there, from there to there? So if I looked at that difference, what I'm seeing is it's not the same as what we had before, where there was a constant difference, but there's definitely a pattern in the difference. So I'm going to look at the difference of the difference and see that from 3 to 5 is a step of 2, 5 to 7 a step of 2, and 7 to 9 is a step of 2. And what I then see is that the second difference is constant. And this is going to be a feature of sequences that have an n squared in their general term. How will this help us? Let me show you. If I'm asked to work out the general term of the sequence, and I don't immediately recognize what it is, I can start exploring it by looking at the difference. Let me do that. When I find the difference between each of the terms, what I'm seeing is it's not a constant difference, but there's definitely a pattern in the difference. So let me look at the difference of the difference. And again, here we see that we get a constant second difference. And that immediately alerts me to the fact that my Tn is going to have an n squared in it. So then I can go and compare what I actually have with the n squared, right, with the squared table. And what I can see here is that in each case what I have is just 1 less than the n squared. 8 is 1 less than 3 squared. 3 is 1 less than 2 squared, right? So whatever's here is just 1 less than the n squared. So my formula for Tn is n squared minus 1. And there's a bit of a similar story that happens when we deal with cubes. So if you're given this pattern 1, 8, 27, 64, 1, 2, 5, if you know this table really well, you'll immediately know that what we're dealing with here is a Tn, which is just n cubed. But let's explore the whole different story in this case to see if there's a way we can recognize these cube patterns very easily if we don't immediately see it. So explore the first difference, second difference, etc. here. Pause the video, try it now, and then we'll see. So did you see this pattern? Nothing to notice in the first difference, but in the second difference we notice a pattern, and it's in the third difference that we get a constant. So if we're given a pattern and we end up seeing that by the third difference we have a constant, we will know the pattern has a cube in it. We're going to look at a couple of other types of patterns. If you have a look at this pattern here, it's very familiar, except for the fact that the problem is you've got negative, positive, negative, positive, negative. How do we deal with that? Well, let me pause on the patterns for a moment, just draw a line under them, and I'm going to do a little work on exponents. Have a look here. Negative 1 to the power of 1 is just negative 1. Negative 1 squared means negative 1 times negative 1. Negative times negative is positive, so our answer here is 1. Negative 1 cubed, you've got negative 1 times negative 1 times negative 1. That is going to be negative 1. Negative 1 to the power of 4, you're going to have negative times negative is positive, times negative is negative, times negative becomes positive again, so you get 1. And negative 1 to the power of 5 is going to be negative times negative, positive times negative, right, etc., etc. You can figure this one out. You'll see that the answer is negative. So this is a very nice little thing we got here. If you notice what's going on, you'll see that if you've got negative 1 to an odd power, the answer is negative 1, and negative 1 to an even power is 1. And this is going to be the tool that helps us deal with patterns of this nature. I can now say that Tn is equal to negative 1 to the power of n squared. Why? Well, the n squared is obvious. 1 squared, 2 squared, 3 squared, 4 squared. The negative 1 to the power of n is because this here is term 1, this is term 2, this is term 3, this is term 4, this is term 5. And whenever I have an odd term number, an odd n, I want to have a negative. And we know that negative 1 to an odd gives you a negative. And whenever I have an even n, I want a positive, and we know negative 1 to an even gives me a positive. Pause the video and try this one for yourself. Establish what Tn would be equal to in this case. Maybe you said Tn is negative 1 to the n cubed, following on what we saw last time. The n cube is definitely right. The one issue here is that this is different to the last time, because this time when n is odd, we want it to be positive. And if n is odd, this is going to be negative 1 to an odd, which will be negative. To correct for that, we just need to put in a plus 1 here, because then when n is 1, for example, you'll have negative 1 to the 2, which will be positive. And when n is 3, for example, you'll have 3 plus 1, which is 4, negative 1 to the 4 is positive. The last sequence we're going to have a quick little look at is the Fibonacci sequence. It's a very famous sequence, so if you Google it, you'll find all sorts of interesting stuff about it. What's particularly interesting for us is the way it's formed. It's very different to any of the other ones we've looked at. How do you get to the next term? Well, you go 1 plus 1 gives you 2. 1 plus 2 gives you 3. 2 plus 3 gives you 5. 3 plus 5 gives you 8. So what will the next term be? 5 plus 8 gives you 13. And the term after that, 8 plus 13, which will give you 21, and so on, and so on. We're going to have a look at some quadratic equation questions from past exam papers for grade 9. I suggest you get a pen and a piece of paper and work these alongside me, because it'll give you a really good sense of whether you have mastered this section sufficiently for the exams. Here's our first question. Give it a try. What would be your next step? Okay, this one is actually almost like, it feels like a trick question, because in fact they've done most of the work for you, right? It's already there. You've got something times something equals 0. We know when we've got two things multiplied together to give you 0, you either have that equals 0 or the other one equals 0. And then solving this, how easy is that? Quickly do this one. And you should have got 2x is 3, and then x is 3 over 2. And on this side, it will follow a very similar pattern, except first you get 2x is negative 3, and then x is negative 3 over 2. Okay, here's one for you to solve. What would be your first step here? Write it down. Okay, hopefully you saw, got an x squared, that suggests quadratic equation. You're fine because you've got equal to 0 on the right, so what you need to do first is you need to factorize. And so we have an x and an x. We've got to have two things that multiply together to give us positive 12, but add up to negative 7, and that's going to be negative 3 and negative 4. Now, I've gone very quickly over that factorization. If you are not completely comfortable with factorization, you need to go and revise it before trying to solve quadratic equations, because it's all going to rely on the factorization. So you need to be very, very familiar with factorization and be able to do it easily. Okay, next step from here. Easy at this point, right? You just say x subtract 3 is 0, or x subtract 4 is 0, and then that's very simple. You get those two answers. Okay, so first step for this one, write it down. Okay, hopefully x squared triggered the idea, quadratic equation, but we know with quadratic equation we have to have equals to 0 on the right, and so your first line will have to be this one. Now we want to factorize here, and we need two things that multiply together to give you negative 12, but add up together to give you plus 1. So if they're multiplying together to give you negative, it's got to be 1 positive, 1 negative. Let's look at all the factors of 12. It's 1 and 12, 2 and 6, 3 and 4. And it could be that these are the negatives, or you could have the same one, but with these the negatives, and you're looking for a combination there that add up to give you 1, and here that combination 4 subtract 3 is what gets me to 1, and so what I have here is a plus 4 and a negative 3. Again, I've gone very quickly through the factorization. If that isn't comfortable or immediately easy for you, you do need to revise it before going to do quadratic equations. Okay, and then next step is easy, right? You just say x plus 4 is 0, or x minus 3 is 0, and those are very easy to solve. And as always with equations, if you're sort of suddenly doubting, did I make a mistake along the way? You can actually just check by substituting your values back into this side and making sure you get out the right-hand side, right? So let's do a quick little scribble check of that. Is x equals negative 4 really a solution? Well, if we substitute negative 4 in place of x, we get 16 subtract 4, which is 12. Great. We know that then the left-hand side is equal to the right-hand side, so we do have a correct solution there. Let's try the 3. We substitute it in place of x. We get 3 squared plus 3. 3 squared is 9. 9 and 3 is equal to 12, so the left-hand side is equal to the right-hand side, so we know for sure that our answers are correct. Okay, a final question from a past exam paper, and here they've chosen to use m as the variable. There's no problem with that. See if you can write down the first line of the solution. Okay, so got equals to 0 on the right, so there's no problem there. So what we need to do is factorize, and when we factorize, the first thing we look for is a common factor, and here we do have a common factor of 4. So we can pull that out, and we get this. What's the next line? Hopefully the next line was also quick and easy for you, because m squared subtract 16 is a difference of squares. So we get m subtract 4, m plus 4, and that equals 0. And now it's simple. Either m minus 4 is 0 or m plus 4 is 0. And so m is 4 or m is negative 4. And we are done.